Go. Right, Thursday, week 3. Ho, ho. Someone pointed out last time that I said the first assignment would be out this week. Well, obviously it's not going to be, because we haven't looked at MIPS, and the first assignment is a bit of MIPS assembler. So I'll release it next week, and I'll still give you 3 weeks, so we'll make it due 1 week after. I mean, if you look at that schedule on the course outline, very optimistic. I don't know how much we're going to meet that schedule, but I will try it. All right, so the lab. One of the tutors told me that a lot of you were not using the bit operators to do. There's some C library functions that you can use to do this. The whole point of the lab is to use the bit operators, but if you found another clever way to do it, that's okay this time. Next time I'll make sure I'm explicit about that. The quiz, only 1/3 of people have done it. Hopefully you'll all do it by Sunday midnight. I have a consultation on Monday and Thursday. No one's ever been, but that's not the reason I'm cancelling. Today I've got to do something else. So just for today, I won't be having my consultation. And there's a CSE survey coming out next week where you can tell me what I'm doing wrong. You can tell us what the tutors are doing wrong, and then we can fix things. So please fill that out with some constructive suggestions. All right, so today I'll finish off structured unions and other things. It's basically fun with bits and bytes, is what today's all about. And I might get on to starting to talk about machine language at the end today, but certainly that's going to be the focus next week. All right, so speaking of surveys, here's another one which we are required to inform you about. Apparently you've got email. This is a government kind of thing. UNSW always gets slagged in this. I don't know what we do wrong, but you always say we're terrible. So say something nice about us this time. Puts us, doesn't, I don't know what it affects actually. It makes the government like us more. Doesn't mean they're going to give us any more funding or anything, but in any case, that's on the way. Right, here's another famous nerdy things time, not a person. I decided to switch it around. Wasn't going to show you pictures of the people, but pictures of the thing. It's a computer. Looks like you could probably have a family of rodents nesting somewhere in it, because it takes up a whole room and it's probably nice and warm. But it's allegedly, it's hard to tell with all these pictures online whether they're true. It's allegedly the Manchester Mark I. Why is the Manchester Mark I interesting? Because it was an extremely early general purpose stored program electronic computer, one of the first. So remember, a few times I've talked about what happened during the war, and they did some development of computer type systems during the war. After the war, some of the guys who were involved in that stuff, say at Bletchley Park, moved to Manchester, including Alan Turing, and they decided to keep working on this idea of computers that they'd come up with during the war. And so they built this thing, a lot of valves, probably you had to keep replacing the valves, probably blew 2 or 3 or 4 or 5 valves a day. So not particularly reliable. You can see that it had the massive amount of 128 40-bit memory words and some storage, some magnetic storage, which actually, when I was reading about it last night, seemed surprisingly modern. It was a spinning disk that they weren't reading across the top, they were reading the disk as it spun around sideways. So all the magnetic stuff was on the side. Interesting, but it wasn't very big. Some of the other storage, back in those days, they seemed to use cathode ray tubes for storing data, which is interesting. The machine had 30 instructions, and the time to execute an add instruction seems quite long by modern standards. You could program it by flicking some switches on the front panel. Gosh, you've got it easy. I remember the good old days. No, I don't. I do remember feeding punch cards into a machine though. But they could feed programs in on paper tape using a code that an encoding system, we talked about ASCII and Unicode, another coding system that actually was devised by Alan Turing. He didn't build this machine, it was built by these three guys here. Anyway, that was, a forerunner of modern computers, and eventually this kind of design got commercialised, and then of course the technology improved, blah, 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 and we're where we are today. All right, let's get back to some bits and bytes. All right. So last time, right at the end, I was talking about structs and how structs were laid out in memory and how I have to worry about alignments of certain things like ints have to be aligned on a 4-byte boundary. Typically a struct would start on a 4-byte boundary. If the first thing in the struct is a single byte or a 2-byte thing, it could be a short, and the next thing is an int, we've got to make sure that the int ends up on a 4-byte boundary, which means we have to add some wasted space for padding things out to make sure the alignment's right. So if we had some kind of weirdo struct like this where we've got a char, an int, a char, an int, and a char, that's what you're going to end up with in memory, and you've got 1, 2, 3, 4, 5 4-byte words, so it's occupying 20 bytes. If you simply define the fields in a different order when you do your struct definition, this is how it's going to get laid out. You can see that that's 12 bytes. And you might say 8 bytes, who cares? What if you've got 1 million of these things? Then 1 million times 8 bytes is a fair amount of space that you would be wasting with padding that's never going to get used for anything. Someone was suggesting at the end of the lecture that there was some way, some optimizer flag for the C compiler that would automatically rearrange this. I looked around and I looked around and I couldn't find it. The only thing that I found was a warning flag that you could give to the C compiler that would tell you there was a bunch of padding inside one of your structs, and then maybe you could go along and reorganise the definition of the struct. All it involves is shifting around the order that you define the fields in the struct definition. But if someone actually knows a way of getting the C compiler to optimise this structure automatically, let us know on the website. Right, so we did an exercise computing whereabouts the fields were going to be laid out in a struct. So that's done. Another thing that I wanted to talk about too. Sometimes you can talk about a struct as containing a string. Sometimes the string is actually stored inside the struct, like this example down here, and sometimes you might have the string outside. Either way, it looks like a structure that's got an associated string. These two strategies lead to quite different implementations, and I just wanted to take a look at those implementations to make sure that you get what the difference is. So here I've kind of gone backwards, and often I'll give you a struct definition and then give you a diagram to explain the struct. Here I'm giving two diagrams, and I want to work through the process of defining a struct for each of these, and in particular talk about where the memory actually lies. Okay? So that the nodes, let's assume that they're going to be malloced, so they're going to appear in the heap. Where does this appear? Well, it could be in the data if it happens to be a constant string that was defined as part of the program, or if it's some kind of string that was allocated and stored into, then it could be also in the heap. So in any case, let's look at the difference between the definitions of these two things. And now I've got to try and find them in amongst all these things, which, by the way, are in the Lex Week 3 exercises directory. All this stuff's there already. That's not the one. I know. It's in this. It's in this file, whose name is plural. Okay, so there's actually nothing there. I hadn't defined it. All right, so how do we define that first node structure? So let's assume this is node 1, this is node 2. Right, clearly that first structure doesn't contain any space to store the string. All it contains is a pointer to a string which is stored somewhere else. So the string isn't actually contained inside the struct. And the other thing that is in this struct is a pointer to the next node. So here we're talking about a straight linked list node. There's a big difference. Well, one thing that's common across the two things is they've both got a pointer to the next node, but in the second case, the string is actually stored inside the node, so we define it like this. There's a significant difference between those two things. The other thing that you can instantly talk about here, that both these things are 4 bytes, so there's no padding involved. This is 5 bytes. That's on addresses are like int, so they have to be on a 4-byte boundary. So that means we need 3 padding bytes in this context here as well. Okay, so they're the definitions for those two structures in the diagram. How do we initialize them? Okay, in both cases, we're going to have something to create the node. So something like that. Here I'll just assume that the malloc works. I won't bother checking for it, although you always should. Now let's assume, no, let's not assume. I was going to say let's assume that this string is something that is going to persist. Maybe we don't know that it's going to persist. So we want to make sure that this node has a copy of the string that's always going to be available to it. If you simply do something like this, yeah, what's called this here? I keep calling everything the same name. Doesn't matter. Maybe I should have changed the parameter name to something smaller, which is something I commonly do, just to avoid confusion. You could implement things that way, and the other thing that you'd want to do is set the next pointer to null, probably. So this is going to be used in the context of building a linked list of these nodes. If you do that, you're making the assumption that this thing, that the thing that S is pointing to is something that's going to hang around. Now, it's been passed in. You don't know where it came from. For all you know, it might be a string that's stored as a local object inside a function, which means that as soon as the function exits, S goes, well, the thing that S is pointing at goes away. So that's not super helpful. So it turns out a couple of ways you could do it. One is you could work out how long the string is. You could malloc the right amount of space, and then you can copy the characters across. C has a quicker way of doing that. There's a function in the string library called strdupe, which basically makes a copy of the string that's being pointed to by S. Okay, so it does a malloc strillen +1 to allow for the null byte, and then copies all the characters across and null terminates it. So that would be a way to do that. So the reason I had to do this is to make sure that I have a copy that hangs around that I can always rely on being there. Because as I said, if you just take an arbitrary pointer and stick it in the node, the thing that's being pointed at, you don't know where it came from. So it could have all sorts of diseases. Okay, so the other one pointed to a new node of type 2. Would have been quicker to go. Do that. Now in this case, the fact that when we allocated the node, we also got a string buffer as part of the node. So we can copy stuff into the string buffer. And that string buffer is ours. It's part of the node. It's going to hang around as long as the node hangs around. So we don't have to worry about this thing here potentially vanishing. So how we'd set that up is using string copy. I was going to change its name to S, wasn't I? So once again, another one of the string library functions. And so that's going to take the contents of S. Ooh, someone should complain quickly. Oh, and the other thing I forgot to do up above actually. This function returns a pointer to the newly created node. Anyone want to complain about what I've done? How big is this? Well, what was that? Oh, what? No, should it? Why? Oh, yeah, okay. Fine, thank you. Right. Thank you. That's what I was interested in. Yeah. All right. Good point. Should have complained about that earlier. Yep. strdupe actually makes a copy of the string, a brand new copy, all right? I can show you, if you want to see what strdupe actually does, it does this. News. I should call it fake news, shouldn't I? Huh? Yeah, that's too long. All right. Okay, so I malloc enough space to store the string, and because striln tells me the number of visible characters, I have to add one to allow space for the null character at the end. All right. So here I'm giving you an alternative to this, so I can comment that out. So I scan along the original string, and I simply copy character by character into the new string. And of course I need to null terminate it. Okay, so that's what strdupe is doing. It's mallocing some space, just enough space to store the string, and then it's copying a string from wherever it currently exists, making a copy of the string from wherever it currently exists into the new space that I just created. Right? So, yeah.
That second method seems really helpful for you because it's assuming the
Thank you.
there should be a checking method.
Definitely. Buffer overflow. And anything could happen. Yeah, str copy couldn't care less. Yeah. So you need strn copy. What?
No.
What's wrong?
The n copy does not create strings.
What? I'm not
The
creating.
n copy is not guaranteed to create a string.
Meaning? Oh, yeah, sure. I hadn't finished. So you're saying it might not be null terminated. Is that your point? That's fine, that's fine. Ooh. Ooh. Yeah. All right, how would you do it? Would you shank? L copy, what's that? Oh, okay. Ooh, let's see. What's the difference? It doesn't even mention it here. STRN copy. What? There is no L copy. So what are you telling me to use it for? Functions copy at most length if the source is less than the remainder, otherwise just, okay, good point. So this is a very important point here. The way I'm using str copy, the way I was using strn copy there, if I copied the entire string, in fact it says it null terminates if it's shorter. Aha, good. In that case, yeah, I know, that's right. So exactly, that was what I made it for. Actually, let's see if Jishan claims there's an strl copy. Oh, there is. Size-bounded string copying. Okay, good. Oh, well, there you go. Something useful I've learned. So I would have done it because I didn't know about strl copy, right? So that's apparently the modern way to do it. I could have done this. And it would also have worked fine. I would have. Yeah. Right, so the reason I have to do this is I've got no guarantee on the size of that string S. It could be 100 characters long. So you could argue this is a slightly crabby approach to things because I've only ever got a string buffer that's size 5. At least in this case up here, the string can be any length and I'll allocate the right amount of space for it and store it there. But it's possible in some contexts that having a fixed size string buffer like that might be a reasonable thing to do. Yeah. Right, any questions on any of that code? So look at the diagrams, look at the code, and hopefully it will become clear how it works. All right. Here's something possibly naughty. Jashenko will probably yell at me about this too. In some context, oh no, he likes it. That's good. All right. So struct, as we saw in the previous example, the string in the first variant of the node, the string actually lived outside the node struct. In some contexts, it's kind of useful to have the appearance that the thing lives inside the struct, but is actually larger than you can fit in the struct. So the trick here is that you define a struct type and you claim there's some object at the end of the struct, which could be an array, like in this example here, and you claim that the array is 1 byte long. When you malloc the struct, normally what you do is you say malloc size of struct. Okay? You could cheat. You could say, I want to malloc the size of the struct plus a whole lot more into which I can then stick stuff. So effectively what you end up with is something like this. So if I created the structure as it was defined on the previous slide, I'd get a length and I'd get a single character. But if I cheat and I say, actually, I think that might be a buggy. Oh no, right, that's right, yeah, I remember doing it that way. If I allocate that amount of space, why not put the null on the end, is that what you're about to say? And then I allocate enough space to store the string will just hang around at the end of the struct, and I can effectively treat chars, which I defined as chars 1, as chars whatever length I want. And as you can see, the actual array exists beyond the end of the struct. So I've allocated more space than the size of the struct, but that's fine. malloc couldn't care less. It just allocates me a chunk of space as big as I ask for. If I want to interpret the first part of that as being part of a struct, that's fine. What about the rest? Well, I can interpret it however I like. So, neat little trick. Of course, there's a lot of restrictions. You can only have one such component in the struct. You can't have an arbitrary length thing and then another arbitrary, well, you could, but you'd need to manage the internal space all by yourself. You need to keep track of how long each of the components actually was. So, but something like this is possibly useful. The other thing you can get away with here is if you know how long the string is, you don't actually need the null terminator. Now, even so, this is, it's not such a great way to implement things, but there are languages, or there have been languages in the past that actually implemented strings something like this. So some kind of structure that had a length and then the actual characters that made up the string. So how could we do it? We could do it like this, and maybe I'll leave that as what's the time? Yeah, I'll leave that as a tute exercise for next week, I think. So one thing that you might think, looking at this diagram, if I've got something that, if you like, sticks out the end of the struct, what if I allocate two of these structs? Is the end of one going to bump into the next struct? Give me an argument why that's not a problem. The question was, if I allocate two of these structs, it looks like there's potentially going to be a problem because I've got something sticking out of the struct, and if I allocate two structs, what if they end up right next to each other in memory? Correct. Huh? No, there's no padding. Oh, there probably would be. Yeah, sure. If this isn't X length, then malloc will deal with the padding there. But the thing is that I've malloced a certain amount of space. Malloc manages the heap and it understands how much space I allocated. So it didn't just allocate that much space. It allocated that much space, and if I malloc another one of these structs, it's going to put it over here. So there's no danger of these things colliding, but potentially it's a neat little trick that you can use. All right, so we talked about padding and arranging things inside structs. What if we want seriously fine-grained control about how the individual bits within a struct are used? Well, C allows you to do that. You can specify bit fields inside a component of a structure. Okay, so here we've got a struct which contains a single unsigned int, and we're actually partitioning up the bits inside that int. And so we're saying the first bit one bit is going to be given the name first bit. So we'd use it just like we use a normal structure field. So we could say, if we've got a variable x, we could say x dot first bit is assigned either 0 or 1. And it will set that particular bit. We can then say we want another part of that unsigned int to be called next 7 bits, and we want that to occupy 7 of the bits in that unsigned int. Here I'm assuming unsigned int is 32 bits. Okay? And then we could have another component inside that single unsigned int whose size is 24 bits. So if you look at all that, adds up to 32. So I've used all of the bits inside that unsigned int. And I can manipulate them by giving them names rather than having to use bit masks and the kind of things that we've been doing up until now. So you can actually declare things two different ways. I think I prefer this one because it kind of makes it obvious that there's only one unsigned int involved. If you declare it like this, it kind of looks like you've got three ints, right? But you get the same thing whichever of those two approaches you use to declaring it. If you specify some number of bits that overflows a word, then you're probably not going to get them all. If you don't specify enough bits, you'll leave some unused bits inside the struct. Right, so in any case, in both of these cases, regardless of the fact that this says unsigned int 3 times, there's only one unsigned int involved in the structure. Yeah? That's a very good question. I didn't try that. Maybe I can set that for... I'm guessing, but my guess is that let's say we've got some bits in here and you use shift 8 bits, then that field will become 0 and they're not going to end up in this part of the word. I think that's what's going to happen, but write a program to work it out. I'll be playing around with some internal bit stuff in a minute. Right, so you can really do very fine-grained partitioning of how you use the bits in a word, and let me see. Right, so here's a slightly realistic example. So imagine we've got some kind of graphic system and we want to define the objects that are appearing on the screen. And these objects have properties and we don't need 8 bits for each of the colour components. Let's say we only need 5 bits. Now that's probably not true, you probably want 8 bits to get the total number of colours. But if we're trying to pack everything in, then we could allow 32 different values for the red component, so that only requires 5 bits, 32 different values for blue, 32 different values for green, and then we've got this extra bit that's not used for anything, so we can stick in some padding there, or leave it out, it wouldn't actually matter. And let's say we want to identify the graphical objects, and there's going to be a lot of them, so we're going to allocate 16 bits. Okay, so how many bits you allocate is really determined by the number of distinct values that you want to represent in that field. So I've decided that for the colour red, or for the red setting, I only need 32 different values. So 0 to 31 are the only variations of red that I can have. On the other hand, I'm assuming there's a lot of objects, so ident allows for 2 to the 16 different identifiers. And similarly, so this object has 2 different unsigned ints. Okay, I've used all the bits in this first one, and then I'm using all the bits in the second one. So for some reason I've decided colour's not very important, So we don't need a lot of bits for each, but position has to be extremely accurate, so I'm going to allow 9 bits for the x and y coordinates, or 9 bits each for x and y. So, in any case, so that's just simply defining a data type, that's defining a variable of that type, and that's how you'd use it. If I assigned a value like 40 to oval.blue, then that's going to overflow because it knows there's only 5 bits, and the compiler will definitely generate a warning, especially if you give it a constant value that's too large. I suspect that it might truncate any bits beyond the bottom 5 if you tried to do an assignment like that. Yeah. Right, so you use these things just like fields in a normal structure, except you're not dealing with, whole ints or whole chars or whole doubles. You're dealing with individual bits, or you're dealing with ranges of bits within a word. So quite a powerful technique, and this is what the storage is going to look like. We've got those two 32-bit words. I guess one thing to notice too a little bit is the actual words don't have names. Only the individual bit parts of the words have names. So I can't actually refer to this thing here. It doesn't have a name. Part of it's called red, part of it's called green, part of it's called blue, part of it's called 1-bit padding, part of it's called ident. So that's, it didn't reach right to the end there. It's a bit sloppy. Oh no, sorry, it didn't, because I've wasted some bits. I didn't use all of the 32 bits. Now there's an interesting question. Does it lay the bits out like this, or does it lay them out in the other direction? And I think we're going to write some code to check that in a minute, and I think it turns out that it actually lays them out in the opposite direction to what I've written here. So the height bits are actually going to be down here, the width bits will be down here, the x coordinate and the y coordinate will be up here, and the wasted bits will be the top order bits. But we can have a look at that. So why do we care about these bit fields? Well, one place that you can use them is, we've been fiddling around with bit masks and bit operators quite a bit. Haha, pun. And, yeah, I know, it's pretty bad, isn't it? So we've made, once again, unsigned in 32 bits. So we've got a 32-bit quantity called myprivs, and we've got some bits that we're using to control privilege or access to files. So we talked about that before. And if you're using bit strings to do that, then you can specify masks. And if you want to turn on a bit, use bitwise OR with the mask. If you want to turn a bit off, you use bitwise AND with the negation of the mask, and so on and so on. So you can do all these operations using bits, or you could define it like this. You could define it using bit fields. And since all of these things are just a single bit, so it can define whether the owner of the file can read the file by this particular bit here, and whether the owner can write the file, and so on and so on. Okay? So rather than having to use bit operations, I can simply do an assignment of either 1 or 0 to the relevant field, and that'll set 1 bit in the structure, in the unsigned int, in fact. So in both cases, whether it's inside a struct underscore privs, or whether it's an unsigned int, I'm simply dealing with a single 32-bit quantity, and I'm using the various bits in that quantity, and in this context I'm using them by fiddling around with bit masks. In this context I'm simply using the name. Effectively I'm giving a name to that individual bit, and then I can turn it on or off simply by assigning values 0 or 1. If I were to do something silly like try to assign the value 2 here, what do you suppose would happen? Gets back to what Shank said before, that it effectively masks off just the bottom bit. So a value of 2 is 1, 0, so you'd end up assigning the value 0 to it if you tried to assign 2, which is kind of not what you want, so you need to be a little bit careful. So these bitwise structs can be quite useful. Oh, I jumped into unions. All right, so something else that you can play around with using named chunks of memory. Remember that everything we've been dealing with is simply a bit string, and if we're talking about unsigned ints, we're dealing with 32 bits. And we're interpreting these 32 bits in various ways. Sometimes we'll partition them into 8-bit chunks, and we'll treat each 8-bit chunk as a character and interpret things using ASCII. Alternatively, we could interpret it as a 2's complement representation of an integer value, or an unsigned representation of an int, or we might even interpret it as a float. And we know, we saw we've got the exponent, we've got the fraction part, and we've got the sign bit, and they constitute a float. So what unions allow you to do is to have a single chunk of memory and allow you to interpret that in a number of different ways. Basically using something that looks like a struct field name. So in this part of the program I say I want to interpret this object u as an integer value, and say u.intval. And we'll see how it's defined later on. This other part of the program might want to interpret the same piece of memory, exactly the same piece of memory as a string. Or this other part might want to interpret it as a single character, or this other part of the program might want to interpret it as a floating point value. It's the same bit string, but it's just being interpreted differently by different people or different parts of the program. So that's what unions give you. And here's an example of how you can define a union. So once again, kind of like a struct, you can specify a tag. So basically the combination of the keyword union and the tag gives you a new data type. You could use typedef if you wanted to have a one-word name for it. But this defines an object which can be interpreted in these 4 different ways. And we can define an instance of an object like this called myUnion. So myUnion represents, or is, a single 4-byte object. And it's 4 bytes because all of these values were, apart from the char, the largest, the biggest component is 4 bytes long. So the int is 4 bytes long, the string is 4 bytes long, and the float is 4 bytes long. That happens to be 1 byte, but we have to allocate 4 bytes to hold the largest interpretable component. So the way you access it is kind of like what you saw in the previous slide. So if I want to think about the object myUnion as an int, then I say myUnion.intval, and then the rest, the program around that, will see this as an integer, like an integer variable, and I can do whatever I do with an integer variable. If I say I want to interpret this as a float, I write myUnion.floatval, and it will take that bit string, whatever it was, and interpret it as a floating point value. What? Where did that come from? It's not carrying something, is it? Some dangerous. How did it get there? It's just appeared. It's been lurking behind the screen the whole time. Decided to come out. All right. So union definitions look a little bit like struct definitions, but they really lead to something that's quite different. If I define something like this, a struct x and y, two separate fields, both of which happen to be 4 bytes long, I'm going to get a structure that looks like that. So x refers to that component, y refers to that component. If I define a similar looking kind of thing with a union, then I get a single component that I can refer to by 2 different names, and depending on which name I use to refer to it, I get a different interpretation of the bit string that's contained inside. Why the hell do we want something like that, you might ask? Good question. I'll get onto that in a minute. So anyway, here's how you define a union. You give a type and a name for a member, type, name for a member, blah, blah, blah. The type can be any C type, so you could have a very long array and then a whole bunch of ints. That's a little bit wasteful because you've got a very long array. It has to allocate that much space, and all of the other components are very short. Doesn't matter. Anyway, when you define a union like that, the size of the union is going to be as big as the largest component, and you refer to it by uvar.member1. And what I'm trying to show in this last slide is that if I take the address of any of those members of the union, it's always going to be the same because they're all referring to the same chunk of memory, and they're just allowing you to interpret that chunk in different ways. Right, so one common way that these kind of things get used is to implement generic variables. So variables that can assume different types as the program progresses. So here's an example. So typically these things, you don't know what the type is unless you remember that somewhere, okay? If you've got a union, you can just say, oh, now I want to interpret it as an int, now I want to interpret it as a float, now I want to do this, now I want to do that. In this particular context here, we want to set it to a particular type, store a value in there, and we need to be able to remember what type of value we set it to. So in order to do this, you'd need a struct that has 2 components, one of which tells you what the type is, so that's what I've got here, and the other one is the union. So the first thing is the type information, the second thing is just a straight union structure, which is a chunk of bits that can be interpreted in different ways. So in the program here, I'm declaring a variable of this type. Then I say, all right, I'm going to make this variable an integer. So I assign that label to it. And then I assign an integer value to it. And then I can print it out as if it were an integer, which in fact it is. If subsequently I wanted to change it and say, all right, I'm going to take this variable, now I'm going to start using it as a floating point value, then I can change the type and I can assign a floating point value to it, and then I can start using it like a float. Okay, so I've got this single variable, but over the course of the program, it assumes, if you like, different appearances, which is potentially an interesting thing. Now, one thing about this is useful for us to remember, so we interpret the variable in the appropriate way. But if I was to, straight after this, put printf, %f, myvar, fval, then it would just print it out as a floating point value, whatever happened to be stored, regardless of what is stored in this field here. Okay, so that's really just, well, it's important for the programmer to know what was the last type of value that I stored in there so I can interpret it properly. But it doesn't stop you interpreting it in some other random way, if you want. Yeah? And downcasting. Oh, you're talking about, yeah, right. Yeah, good point. Casting, I think there are rules that apply to how casting is going to be interpreted. And it might not be quite the same as what happens here. Here it's clear that we've got a single chunk of memory. I mean, you're right, there are some similarities and potentially you could do it that way. So one place where it is going to be different, if you've got a floating point value and you cast it to an int, I'm pretty sure it does truncation. So you just get the integer part of the floating point value. Here, you don't change the value. If I assign 3.14159, I set the bits in a certain way, and if I then decide to interpret it as an int, I'm going to get those bits rendered as an integer value. So quite different. Yeah. Fair comment. What's the time? 1:56. Oh, damn. Oh, good. Well, I can use this as a tute question for next week. How convenient. All right, so we'll do that. So we talked about floating point values and, you know, the various components of a floating point value. You can actually do it yourself using a union. If you want to have a look at how it's done, the code is already under Lex Week 3 exercises. Okay, go!